Hello everybody. In this video we're going to start talking about the equations that we can use to estimate the diffusion coefficient in different phases. So we will have we will start first by the estimation of the diffusion coefficient in in the gas phase, and then in the liquid phase, and then in the solid phase. And again, I want to emphasize on the point that these are many equations because each of them is suitable for a specific system, and we will talk more about these differences when we go into the details of these equations. So we will start with the diffusion coefficient equations for gas phase. And first we will start with a theoretical background about the estimation of the diffusion coefficient, and this is important because it gives us some insight on some relations between the diffusion coefficient and the parameters that affect it. So the first or the theoretical equation that has been put to estimate the diffusion coefficient was based on the kinetic theory of gases. And it's like a long theory, but the point that is important for us is that it assumes that the gas molecules are spherical elastic spheres, and these elastic spheres collide elastically, which means that they bounce without losing energy. And this is the basis of the equation that we are discussing now. So the equation assumes that a very hypothetical case that we have a gas A that is diffusing through its isotope A star. So as we all know, the isotope is the same element, but it has different atomic weight because it has different number of neutrons. So it has the same number of protons and electrons, but just the number of neutrons is different. So the molecular volume in both cases is the same, and that's why this is a very hypothetical case. Just a hypothetical case where the two species A and A star, which is A and B, the diffusing species and the medium that it's diffusing in, are different, but they have the same molecular volume or atomic volume. So based on the kinetic theory of gases, the diffusion coefficient can be estimated to be, or can be calculated using this equation, where the diffusivity of A in A star equals 1/3 multiplied by lambda multiplied by U. The lambda is the mean free path of the length of species A, and this means that any gas molecule that is diffusing or moving from a point to another, it doesn't go directly in straight lines. It goes in like a wavy shaped pattern or path, and the amplitude of this wavy path is what we call the mean free path of length of species A. And U is the mean speed of species A with respect to the molar average velocity. So this is the average velocity that we discussed before. And I'm not going to go into details of the theory, but from the theory states that lambda can be calculated from this equation and U can be calculated from this equation. Some of these parameters are known, like the T is temperature, P is pressure, MA is the molecular weight, but some are kind of new, so I'll discuss them quickly. So if you plug these two formulas in the main equation, the final equation will look like this. And here we can find that the N is the Avogadro's number, P is the pressure, T is the temperature, M is the molecular weight of the diffusing species, and K or kappa is the Boltzmann constant. It's like a very well-known constant, so it's just a constant. And sigma A is what we call the Lennard-Jones diameter of spherical molecules. So this is kind of way of describing the molecular volume or the molecular size, which is the diameter of spherical molecules. And this equation was manipulated so that it can fit with two species A and B that have different molecular volumes. So it's almost the same, but it has, as you see here, this molecular weight and this sigma terms are different now. It's still directly proportional to, or we have T power 3 over 2 N power half as we had here, like the same, and the K power 3 over 2, and only this is the difference that we can see. This equation is not like used to estimate the diffusion coefficient because it's based on assumptions that are not valid, which are the elastic collision between the molecules, which is not the actual case, because we in real life we see attraction and repulsion forces between the molecules due to the bonds that form and different things that take place. But the good thing about this equation that it gives us some idea or more accurate idea about the relations between the temperature, pressure, and the diffusion coefficient. So from this equation we can notice different or more than one observation. So the first is that if I switch A and B, if I say the diffusion coefficient of B in A, the equation would be the same because it's 1 over 2 MA plus 1 over 2 MB. So it doesn't matter if I put MA before MB or the other way. The same for sigma A and sigma B. The rest of the terms do not take into account any of the parameters related to the diffusing species or the solvent medium. So this means that the diffusivity of A in B equals to the diffusivity in B in A. And this is not right for liquids or for solids. It's only valid for gases. The second observation is that the diffusion coefficient is directly proportional to temperature per 3 over 2, and it's inversely proportional to pressure. And this is something we can get logically. So of course, if you increase the pressure, then the molecular spaces would be smaller, and then the diffusion would be more difficult. So as pressure increases, the diffusion coefficient will decrease. It's very logical. And the same for temperature. If you increase the temperature, the molecules gain more energy and the spaces increase, so you have easier diffusion. So it makes sense as well that the higher temperature would make or will lead to high diffusion coefficient. But this relation, to know that it's inversely proportional to pressure and it's directly proportional to temperature power 1.5, this is a good thing. The other thing is the relation between the diffusion coefficient and the molecular weights and molecular volumes. So high molecular weights will lead to lower diffusion coefficient, which is logical as well, and the same for the molecular diameters. As they increase, the diffusion coefficient will decrease. So this is like the main take-home message out of this equation. We're not gonna use it again because it's based on theoretical or on some assumptions that are not valid, and that's why in the next video we are gonna start talking about the actual equations that we use to calculate the diffusion coefficient. So we will continue the next video, inshallah. Goodbye.